Have you ever wondered what lies beneath the surface of everything around us, from the salt in your food to the ink in your pen? What if we kept breaking things down into smaller and smaller pieces? Would there be a limit? Well, over 2500 years ago, Indian philosopher Maharshi Kanat proposed something truly visionary, that if we keep dividing matter, eventually we'd reach particles so small they could no longer be divided. He called them Parmanu. Around the same time in Greece, Democritus and Eusebius suggested the same idea, calling them atoms, meaning indivisible. Of course, these were brilliant ideas, but without experiments, they remained theories. It wasn't until the 18th century that chemistry moved from imagination to investigation and the first true laws of chemical combination were born. Now imagine a chemistry lab where scientists were still arguing whether air had weight. That was the world before Antoine Lavoisier stepped in, often called the father of modern chemistry. Lavoisier didn't just theorize, he measured. He performed careful experiments and introduced the idea that chemical reactions must be studied by tracking mass. This changed everything. He formulated two of the most important laws in chemistry: the law of conservation of mass and the law of constant proportions. This shift from mystical alchemy to measurable science is why we remember Lavoisier as the man who truly brought precision into chemistry. So let's explore Lavoisier's first great insight, the law of conservation of mass. This law says matter can neither be created nor destroyed in a chemical reaction. Let's take a chemical example. Barium chloride reacts with sodium sulfate. The equation looks like this: BaCl2 plus Na2SO4 gives BaSO4 plus 2 NaCl. Now, what's amazing here? The total mass of the reactants, that is, barium chloride and sodium sulfate, is exactly equal to the total mass of the products barium sulfate and sodium chloride. No atoms are lost. No atoms are gained. They're simply rearranged. You don't have to just believe it, you can actually see this law in action. In your textbook, activity walks you through it. Picture this: you have to solve solutions in separate containers, say barium chloride in a test tube and sodium sulfate in a conical flask. You seal the test tube and place it inside the flask. The whole thing is corked and weighed. Now shake the flask so the solutions mix. A white precipitate forms, that's barium sulfate. But here's the kicker: when you weigh the flask again, the mass hasn't changed. This proves that even though a chemical reaction has occurred, the total mass before and after remains the same, just as Lavoisier predicted. This is why we say mass is conserved during chemical changes. Now let's talk about Lavoisier's second insight, the law of constant proportions. This law says, in a chemical substance, the elements are always present in definite proportions by mass, no matter where the compound comes from. Take water, no matter if it's rainwater, seawater, or boiled water from your kitchen, it's always made of hydrogen and oxygen in the ratio 1:8 by mass. So if you decompose 9 grams of water, you'll get 1 gram of hydrogen and 8 grams of oxygen. Every single time. Or look at ammonia, nitrogen and hydrogen always combine in a 14:3 ratio by mass. This consistency is what allows chemists to know exactly how much of each element to expect in a given compound. It's the chemistry of certainty. But why do these laws work so perfectly? To answer that, we need to fast forward to 1808 and meet John Dalton. Dalton took the philosophical idea of atoms and gave it a scientific form. His atomic theory explained why the laws of mass and proportions hold true. Here's what Dalton said: all matter is made of tiny, indivisible particles called atoms. Atoms of the same element are identical in mass and properties. They combine in simple whole number ratios to form compounds. Dalton's model gave structure to the invisible. It told us that the reason mass is conserved is because atoms are conserved. And the reason proportions stay constant is because the atom ratios are fixed. Let's quickly revise what we've learned about the laws of chemical combination. We began with ancient philosophies from India and Greece, then moved to Lavoisier, the pioneer who brought measurement into chemistry. His law of conservation of mass showed that matter isn't destroyed, it's just rearranged. Then Proust's law of constant proportions told us that compounds always form in fixed ratios. Finally, Dalton stitched it all together with his atomic theory, revealing atoms as the core players in every reaction, obeying these rules silently and consistently. I hope this session helped you see how chemistry is not just a subject, it's a language the universe uses to build everything from stars in the sky to salt in your food. Catch you in the next class where we dive deeper into atoms and their structures.